Woohoo, and welcome back. Today we're in section 310, and we're going to be talking about linear approximations and differentials. For this video, we're just going to focus on linear approximations, and there'll be other videos talking about differentials, which are totally cool too. So we're going to start off with, what the heck is a linear approximation? Well, basically what we're going to do is we're going to use the tangent line, but make it super formal. And so everything we're about to do is going to feel just very mathy, but it's really just kind of rewriting the stuff we've been doing since the beginning of taking derivatives. So let f of x be a differentiable function. You got to be able to differentiate. What is the equation of the line tangent to f of x at x equals a? So we're looking for the tangent line. And that has been what we've been doing from the beginning. We've been finding points and drawing the tangent line. But now what we're going to do is we're going to find a line that has a very particular formula. So what sort of things are happening? Well, we know that if x equals a at this point, we know that the y value is going to be whatever the function value, if this is f of x, that point has to lie on the function f. So the y value is going to be f of a, and the x value is going to be a. So we want the point a comma f of a to lie on the tangent line. And we want the slope of the line to equal the derivative, right? That's what we've been doing since the beginning. The derivative is the slope of the tangent line. So now we're going to do some very formal math, and we're going to start off with a form of a line that a lot of you haven't used a lot. This is called the point slope form. And remember that a lot of folks have actually chosen throughout this class and in algebra have chosen to use slope-intercept. That's a different one. That's the one that looks like y equals mx plus b. So that's a slightly different form. We're going for a more mathy, more formal line, and it's called point slope. You can see there's the slope and there's the point, the y1 and the x1. And so now through the magic of television, we're going to say, well, we want the slope to be the derivative at the point A. We want x to be the point A, and we want y to be f of a, right? Everything that we talked about over here, we now want to plug that into the equation. And then the last thing that we do is we add f of a to both sides. So I add f of a over here, and I add f of a over here, and I end up with this that no longer looks like the equation of the line. In fact, it looks like some sort of nightmare creature that crawled from under your bed. But I promise you, this is really just y equals that y value plus the slope times x minus the x value. So it's just a very formalized way to look at the tangent line. And so we're going to go through the steps to find this. And when we do, we're going to call this the linearization of f at a, which sounds so fancy. But basically what we're saying, take your function, make it a line. Now, can we actually take any function and make it exactly into a line? No, and we've been talking about this the whole way through. When we do this, find the tangent line, this line is a good approximation if we look really close to the point of tangency. They're really close. But as you get further and further away, like in this case, if this is a parabola, the function is going to head down where the line just keeps going up. So we're not going to be able to get a perfect line that's going to match the function exactly. But again, close to the point of tangency, it's going to be close enough. And that's going to help us with other things we're going to do. So, you guys ready? Let's do it. Okay, I picked a nice, juicy function, x to the 3/4. And you're going to say to yourself, what is that? And I'm going to remind you that that's what happens when you take the 4th root of x cubed, or you take the 4th root of x cubed. And as long as it is as long as it's a real number, these two are equivalent. So this is some pretty interesting stuff that's happening. X to the 3/4. So what do we do? How do we go through the process? And the answer is, this is going to look exactly like what we've done to find the tangent line. It's just a little bit more formal. So the first thing is, if we know we're going to do it at x equals 16, we need to find y. And this is going to connect up with this point, number 1 up here. So I'm going to call this number 1. And this is going to be when we find the y value. And so f of 16 is 16 to the 3/4, which is equal to the 4th root of 16 cubed, or it's the 4th root of 16 cubed. Off the top of my head, I don't know what 16 cubed is, so I'm going to use this one. We will get the same value. And so what is the 4th root of 16? So you got to think, what to the 4th gives me 16? That's 2. 2 times 2 is 4, times 2 is 8, times 2 is 16. So that's 2 cubed, which is 8. So that's where we begin. We've got the point, and that's the point of tangency, is 16, 8. That's where we've got the tangent, the line is tangent to the curve. Okay, so that's the first part. The second part, we want to find the slope, right? Because to find a line, either we need 2 points or we need a point and a slope. And we know that the slope is going to be the derivative at that x. So at x equals 16. So let's go ahead and look at the equation. F of x is x to the 3/4. So the derivative of f at x. Now remember, we're going to have the power rule. We're going to have 3/4 come down, and then we're going to subtract 1. So that's 3/4 x to the negative 1/4, or 3 over 4x to the 1/4, which is going to be 3 over 4. Now this is going to be a little tricksy to make sure your 4s don't bunk into each other. It's the 4th root of x. And so we want to find f prime at 16. So that's going to be 3 all over 4 times the 4th root of 16. Now from above, we know the 4th root of 16. That's 2. So 4 times 2 is going to be 8. So we've got 3/8. So that's our slope. Okay, so far so good. We've got a point, 16, 8. We've got a slope, 3/8. So you're going to go through these 2 steps for every time you want to linearize, or the linearization of f. At this value, you're going to find the point and the slope. Now I'm going to go to the next page because I've run out of space. So then, just to review, I've got the point 16, 8, and I've got the slope, which is 3/8. And so the linearization of this is technically going to be f of a plus f prime of a times x minus a. So the linearization, yes, of f of x at x equals 16 is going to be y equals f of 16 plus f prime at 16 times x minus 16. F of 16, that's the y value. That's 8. F prime of 16, that's the slope. That's 3/8. And then we've got x minus 16. Now, technically, that's the formal way of writing it. You can also multiply, and if you do, you'll get to slope intercept. So what does that mean? Well, so this is the linearization, and frequently we stop here, but if you kept going, the 8 cancels the 16, and we end up with minus 6. So y equals, oops, sorry, you can't see that. Y equals, so if I multiply through the 3/8 times each of those, and then I cancel, I get 6 over here, and 8 minus 6 is 2, so then I get 3/8 x plus 2. This is the slope intercept form of the tangent line. And let's see if I can get these both in here, kind of, almost. I wrote a little bit too big, so can I kind of squish this down? Oh, I'm Ken Burns again. Okay, so up here, this is the linearization. It's a very formal way to write it out, and a lot of times we leave it in this form because that gives us a lot of information. That gives us the y value, that gives you the slope, and that gives you the x value. So you get a lot of information here. If we multiply out, the number 2 doesn't really have anything to do with the other values that we use to come to this point. That's the y-intercept of the tangent line. So that's the point where the tangent line hits the y-axis. That's not necessarily the most important thing about this. So in this case, we're going to leave it like this, but it really is the same work, just a slightly different order that we did before when we found the tangent line. So, woohoo, yay! So just to be clear, I kept going just out of curiosity, but when you do these problems, go ahead and stop right there, unless the problem asks you then to continue to get the slope intercept form, the y equals mx plus b form. Okay, wow, that was really quick. I don't even know what to do when the video is only 13 minutes long. I guess we could just sit here for another 10 minutes awkwardly, or I could go ahead and say, you know what, get up, go out, touch some grass, find those people that you love and tell them you love them, call your parents, or just go into the other room and say howdy if that's a possibility. And if you say howdy, they'll probably laugh, but say hi, whatever you normally say. Don't get too weird, don't let on, they'll figure it out. Go out and or stay in, but do something nice, and then come on back because we've got to deal with differentials. The next video, I'm not gonna lie, it's gonna be kind of weird. If this wasn't weird enough, this is gonna bring the weird. So for the next video, make sure you refill your water. I've got my water right here, so that my voice sticks around for the next, however long the next video is going to be. But, get something to eat, get a snack, wiggle your body a little bit, and, take care of yourselves. Maybe even take a nap, and then come on back, and then we're going to talk about differentials. Super cool, super weird, and I guess all that's left to say is woohoo and math on.